Thank you for the introduction. So I'll directly start. This is a work of my PhD student, Grzegorz Glodek. He is not here, unfortunately, but I'll try to cover part of the work that he did for his PhD topic. I will not talk about the additive manufacturing. I mean, the basics is well known, but just briefly that, okay, we studied powders, laser, we repeat the process, we make a part. Industry is using a lot this technique nowadays. They are accelerating their activities mainly because of some added values like 50%. At least they mentioned that on their websites, 50% reduction of the lead time, flexibility that they get, 75% less development and these kind of things. But the issue is, is the structural integrity of these materials at the level that they can be used in the final application. Of course, there have been a lot of work on, let's say, fatigue and fracture behavior of these metals, but when it comes to complex applications such as this dovetail joint, which is being, let's say, inserted in a turbine blade, which is inserted in a disc, what are the conditions here at the contact interface? There we have more complex situations. We have a tribomechanical response of the material. In particular, we are talking about the laser point, fretting fatigue. So the idea of this PhD was, can we find out what happens to AM material like Ti64, which is being used a lot for this application? So I'll try to provide some answers to this question in this talk. I'll briefly talk about fretting fatigue and mechanical behavior of materials in that harsh environment. And then I'll talk about the experimental setup and numerical modeling that we are developing and some results and discussions. And we will see if we can provide some answers in the conclusion. So let's start with the basics of fretting fatigue in this particular application. Fretting fatigue happens in many applications, bolted connections, riveted connection. But in this particular application, we have blades. It could be a kind of dovetail shaped blade or a fir tree, let's say, blade disc attachment. At the contact interface here between the let's say the blade and the disc, because of the two loading conditions that we have, tensile load and vibration, we get some local stress distributions. For both cases, this local stress distribution causes a contact load and also a shear load. This combination of contact load and shear load generates a very complex loading conditions at contact interface, in the way that the middle of the contact is sticking, and at the edge of the contact, we have partial slip at the micro level. So what happens there? The crack starts here because of the micro fretting, and then the crack propagates through in the mixed mode because of the contact situation and the shear stress distribution that we have here, and then propagates through the root of the blade. And then that causes the final fracture. So the main objective of this PhD work was to set up a kind of testing and numerical framework that we can test such a difficult condition in a controlled way. So that was the objective of the work. I will start about with the print job. So it was a very big print job. So I'm not going to talk about all the tests that we did. These are the parameters that we use just to give you an idea of, okay, these parameters are already optimized. And I think we have launched 3-4 PhDs during the last 3, 4, 5 years in collaboration with Siemens to find the optimum parameters for this material. But some of the important parameters is at the end, we got 99.66% density, and also the roughness is very good. We did also, let's say, the heat treatment. We used 2 different setups here. You see the dovetail blade setup and also the bridge type setup, which is suggested, I mean, some recommendations by ASTM standard. Today, I'll not talk about this because of the time limitation. I will focus only on, as I call it, the semi-component level testing. So some basic material properties before we start doing fretting fatigue test. We wanted to know that the material is strong enough, at least comparable with the data that we have. We see that it's very typical behavior, so more elongation, less tensile stress, and let's say the ultimate stress, and also the modulus of elasticity is lower than the wrought material here. From a microstructure point of view, we found a typical alpha beta, let's say, structure, which is very common for this kind of 3D printed materials. Again, we did not see any sort of abnormality related to microstructure that could jeopardize the results of the fretting fatigue test that we do. Here is the setup that we try to develop. So this is the fixture. So we have two contact pads, which are, let's say, representing the blade. And we have a dovetail shaped sample, which is representing the, so here it's the disc, here it's the blade, actually. Here are the details and the geometrical parameters of the, let's say, the blade and the pads that we use. We use complete contact, and incomplete contact. One of the critical parameters here is this angle. So if you search in the literature, it can vary between 35 to 55, depending on the type of the engine, depending on the final application. But that can play a crucial role when it comes to fretting fatigue, because that can cause, let's say, fatiguing of the sample at the wrong spot. Yeah, you can have a kind of competition between fatigue and fretting fatigue. That's the reason that we selected the lowest, let's say, angle, which could cause more stress concentration in our part, just to check the capability of AM materials. And then we cycled the sample with a stress ratio of 0.1 and the frequency of 25 hertz. And these contact loads are generated by the axial load, and that's why they are also cyclic. So this is the basic setup. We also developed finite element simulations just to control the load level. I'll tell you why we started with finite element model, just to find out what would be the contact status at the contact interface to avoid overloading or staying at the partial slip regime, which I will explain. So there are three critical points. One, contact interface, which we expected to crack initiate there. There are two, let's say, transition areas. With the finite element model, we can see that there is a huge difference. I mean, there are at least 200 megapascals difference. And normally, we do not expect to have any failure here based on the finite element model. But it's AM material, we will see. And for the accuracy of the model to rely on these results, we did also some calculation. We got the global slip amplitude, so the average is the displacement here, and then we got the global slip, and then we compared that with the experimental DIC results just to make sure that we are using the correct frictional parameters. And then we did some simulations, and then we found out that the 0.55 is the correct, or at least reliable coefficient of friction that we can use. Here are some stress distributions, which are very typical for fretting fatigue. So here is the tangential stress distribution at contact interface, and this is the leading edge of the contact, which is closer to the side that we apply the load, which the stresses are higher. And here, what you see is the shear stress distribution, frictional shear stress distribution. That's the indication of partial slip conditions. So we have the sticking in the middle, and we have slipping at two sides. So that also confirms that the loading that we are selecting for our test is in line with the more damaging parameters or scenario. So just to make sure that our setup was, let's say, performing very good, because, I mean, a little bit of misalignment could cause a lot of problem. So what we did, we just did DIC. So we did one full cycle and used DIC, but we did at different cycles. First cycle, 1,000 cycles, and 100,000 cycles. Of course, you cannot compare it one by one, but the first cycle and the 5 cycle is important because we are applying the maximum load. If we focus on these three actually figures, we see that let's say the displacement is more or less staying in the same even after 100,000 cycles, and we don't have any misalignment, or we don't have any rotation in the setup. We did also calculate the slip amplitude at two sides, just to make sure that we have a kind of overview of what happens at the contact interface, and we see the evolution of the slip. And after around 100,000 cycles, we have more or less the same slip amplitude with the difference of 0.1 micrometer at two contact sites. Here are some results. So let's talk about the results. First, what we did test and we plot the forces against the number of cycles. What you see here, they are grouped in two cases. So we have rod material and AM material, and we have some fretting fatigue, and some of them which are failed outside of the contact. When we say outside of the contact, it's in the transition area, and mainly in this neck area. So for the rod material, we could explain it, because according to the finite element model that we had, so if we apply higher stress levels, then we are not having most damaging contact situation, and the stress shifts to the neck. I will show you a graph later, and I'll explain why. But for AM material, we found already the proper loading condition, which should not cause any extra stresses, but we had at least 2 or 3 failed outside of the contact. So it failed not here, but here. I'll dig into it later. And then we try to compare the data with the available data from literature, from NTNU, from Purdue University in the United States, which they use the same material. Of course, with the force displacement, with the force number of cycles, we cannot really compare them together because the geometry, the material, they are different. So we try to gather them together. Let me see. Oh, should I go ahead? Okay, I'll try to keep it quicker. So then we have here the stress distribution, maximum principal stress distribution range, and then we see that your closure, and then we have here the slip amplitude. But again, we see that the slip amplitude is also a very important factor at contact interface. Then we define the kind of effective slip amplitude, which gives us an overview of the stress distribution at contact interface, plus the slip amplitude, which are very important in this case. And in this case, we see that, okay, there's a kind of good agreement, except a couple of tests that they did at Purdue University, which they were run out actually, and they did not provide a lot of information about their tests. So let's talk about the focus on the AM part. For the rod material, the reason that I said that this is very typical because of this graph. This graph shows a relationship between tribological and mechanical behavior of materials when it comes to fretting fatigue. This is the damaging part. So at this point, we have the minimum damage, and if you increase the load or displacement, then the wear will remove any crack from the surface. So the crack does not get the chance to propagate. And that's the reason that for rod material, if you overload the sample, so if you apply higher load levels, there wouldn't be any damaging. That's why the crack initiates there. But for this optimum 2 load levels, the reason that we had these 2 failures should be investigated. So that's the reason that I'm going to talk about 3 of these, let's say, failed samples. The first one was fretting fatigue. So here you see the contact interface, so sticking area in the middle and slipping area in the edges. If you look at the micrographs, we see that the crack initiated at the surface. The microscopy is also confirming the same. For the samples which did not fail at the contact interface, we have this distinguished slipping situation, but we saw that the crack initiated at the edge, but we found some kind of defect induced by manufacturing process probably of the AM, but it's more sensitive than the rod material. For the other one, we found a big lack of fusion close to the surface, which caused actually the crack starts in the neck area because the stress was higher at that point. We have found also some, let's say, secondary cracks, which there was a fretting fatigue crack, but also cracks starting at the neck area. So here you see another example of subsurface defect. We did also some simulations to confirm that. 2 more slides, and we used continuum damage mechanics. And the main reason for this simulation is to understand the behavior and integrate actually the defects inside the finite element model for crack initiation. And also we try to estimate the crack propagation path using standard finite element model, and adding all together, you see that we can predict the results well compared to the AM material. And the next step would be integrating these defect-like features in the simulation. So the takeaway message is additively manufactured material, a lot of data on fatigue of these materials are available, but we have to test it in the real condition. Definitely fractography will help us to understand the root cause, and then my finite element model will help us to understand the effect of these defects on the fretting fatigue behavior of AM material.
Thank you.